Okay, so I'll push aside parity. We saw the idea we could do orthogonal modulation. Orthogonal modulation, that's a way of trading off bandwidth efficiency for bit error rate efficiency, just like we did for FSK. It's just that the structure here we did in the time domain, and we interpreted them as codes. Now what we're going to talk about is real forward error correcting codes. So not using this orthogonal, but trying to find out with some kind of redundancy which is efficient, that allows us to get better performance, but not being so profligate with the with the spectral efficiency, not paying too much in spectral efficiency. So first of all, I'm just going to talk generally now before we get into specific error correcting codes. So let's just look at the bit error rate curve for coded and uncoded systems. So what I see here in the solid curve here is the uncoded, typical. This maybe is BPSK. And what I'm going is, so of course it's EB over N0 versus the bit error rate. Now what do you see in the dotted line is now the coded rate. And you remember, it's better if it's closer to the origin. So the coded rate is better because it's closer to the origin. And there's kind of a couple ways I can look at that. For instance, let's look at a compromise where I go from, what is this, point A to point C. Point A to point C is lined up on top of 8 dB EB over N0. So I'm stuck with this EB over N0. That's what I'm living with. If I don't use coding, I'm going to get 10 to the minus 2 of errors. If I use coding, I can get only 10 to the minus 4 errors. So I'm getting better probability of error, but of course, when I use coding, there's going to be something to pay in bandwidth efficiency. Another way I can look at it is how much signal to noise ratio do I need for a given quality of service. For instance, suppose I want 10 to the minus 6 as my bit error rate. Well, if I don't use coding, then I'm going to be over here at point D, and I'm going to need something like 14 EB over N0 in order to achieve that 10 to the minus 6. But if I pay the cost of error correcting codes, both in terms of paying in terms of complexity, paying in terms of bandwidth, I can get that down to only requiring 9 dB for EB over N0. And we call that the coding gain. So that's the gain when I use an error correcting code. In this case, it would be something like 5 dB coding gain because I'm using a code. So remember that on these curves, we cannot see what we're paying in bandwidth efficiency. Okay, we can only read on these curves the improvement in bit error rate. For instance, suppose that we're not using coding. We're sitting here with performance of 10 to the minus 6, and I just want, if I go with faster transmission, so I was doing 1 kilobit per second, and now I go to 10 kilobits per second. Because I'm going to 10 kilobits per second, of course, then I'm going to expand the bandwidth, but that would let in more noise, and maybe I would not get good. I would get worse performance. But now I add an error correcting code, and then I can go all the way down to E and get the same performance. So that gives you an idea of where you're trading and how you're getting your gain. But let's look at a specific numerical example to see that. But before we do that, one step before we do that is to look at the place in the curves where the dotted one is not closer to the origin. That there's some crossover region, and that's where coding can actually make your performance worse. So why would I use a code if it was going to make it worse? Well, the answer is I don't use it. I don't use it in this area. I only use my error correcting codes if I'm down here. But you know, why does it cross over? That's one thing we'll see in our numerical example. Oh, by the way, we call this the FEC limit. It's the point for the probability of error, uncoded, where if we add forward error corrections, we'll actually get an improvement. We also call this the forward error correction threshold sometimes. So I'm going to take a very simple example. Suppose I have EB over N0, it's 9.6 dB. That's in dB, and in linear, that would be 9.12. So I take this equation for BPSK, and I go and say, well, what probability of error will I get at 9.6 dB? So I'm looking over here on that uncoded rate, and I see that I would get something like 10 to the minus 5 is my bit error rate. Now I'm just going to tell you that I have a code, and this code is special. It turns it into 11 data bits. It turns into 15 coded bits. And my little magic forward error correcting codes, whenever there's only one error in the block, I fix it. Every time. Doesn't matter where that error is. If it's in any one of these 15 bits afterwards it's transmitted, I'll find it, I'll correct it. That's the way this code works. Okay, so let's just take these numbers. What does that mean? Well, first of all, there's the bandwidth expansion. When I would normally only have to send 11 data bits, now I have to send 15 data bits. So I have to send it faster. If I send it faster, it takes up more bandwidth. So there's like a 36% increase in the bandwidth. Then when I ask the question, well, what do I get? I'm paying 36%. What do I get? Is there a bit error rate improvement? How would I know that? Just given this data, how do I know if this code is going to actually improve things for me? So we'll go through the math. So what is the probability of having at least one error in k bits when I don't have coding? Okay, so I'm not using any codes. I just got my k bits, no redundancy added. And I want to know, well, how often is it going to happen that I'm going to have an error at all? Any number of errors, one error, two errors, however many errors. There's going to be an error. That's 1 minus the probability that there are no errors. That's easy to calculate. It comes out to be something around 10 to the minus 4 for this example. Now I want to say, same question, but when I use coding. Okay, first of all, I have to change, because the EB over N0 that I have here, 9.6 dB, that's when I'm only sending those 11 bits. When I have to send 15 bits, I also have to take the energy and spread it over 15 bits instead of spreading it only over 11 bits. So that means that I take a hit right away on my EB over N0, and I call it encoded over N0. So EB over N0 is no code, and now I have to reduce it because of this redundancy I'm adding. So in the case of this code specifically, 11 data bits, 4 parity bits for a total of 15 coded bits, I end up having only 8.3 dB instead of 9.6. So I take a hit because I assume that I have the same energy budget, and I just have to spread them over more bits. So for the coded block, for that value now of 8.3 dB, I calculate the probability of error, and now it's something like 1.3 times 10 to the minus 4 instead of 10 to the minus 5. So before I do any correction, the bit error rate actually is getting worse because I have to spread out my energy across more bits. Now I ask the question, I know that a block with one error will be corrected. So the only time that I'm going to get an error is if the errors occur not one but 2 or more. So now I calculate what is the probability that I will get 2 or more errors per block. And in our example, that comes out to be about 1.94 times 10 to the minus 6. So, did I get coding gain? Yes, I did. In a block of 11 bits, the probability that I would have some kind of error, in this case it was 1 or more, was 10 to the minus 4. But now when I use the coding, the probability of getting some kind of error, in this case it's going to have to be 2 or more, because the 1 is going to be corrected, that's only 10 to the minus 6. So I have like a factor of 60 improvement in my probability of having some kind of error when only paid 36% in the expansion of bandwidth. So we did get improvement. So that means that we're somewhere down here, which makes sense. I said that we were using 9.6. So we're in the good region where the dotted curve really is close to the origin. Now, what would have happened up here? Why would it not work? Why would I have this crossover effect if I'd started up there? Well, the reason is when we were doing this beginning point, our beginning probability of error would have been really, really bad, okay? Because I would be starting over in that other region where there's a lot of errors in the begin with. And then when I take the hit on the coded error it would really, really be bad, and I wouldn't get an improvement. So it just means that the channel has to be pretty good, so that when that first step with the BER worsening, if it gets too much worse, well then things fall apart. And that's why we have a FEC threshold.